Hi there. Well, this is just an appendix of part 2. So I'm just going to quickly explain how we can reach the same results that we've presented in part 2 from a slightly different perspective. And then from this perspective, I'm going to derive this efficient second-order optimization. And you're going to see that it's a very simple idea, and you can easily understand it if you understood the framework that I presented earlier. So we've shown in part 2 how to find the optimal value for the parameters p, which minimize the sum of square differences, and we did that from a Newton-style perspective, right? So we did the first derivative on top of the second, and we found the increment delta p, which is added to p and minimizes the function f, the sum of square differences. So this is the equation for the first derivative, and this is the equation for the second derivative. And we saw that we can ignore the second term to obtain an increase in the convergence basin. So this is the Gauss-Newton approximation. So this was all explained in part 2. You can check it if you have any doubts. You can also check for the meaning of all these, for the notation basically. So if you have any doubts, you can just click on the video and see the explanation for how we reach these equations. Okay, so now let's see if we can reach the same result from a slightly different perspective. So instead of using that update equation that I've presented earlier, let's rewind and remember why we're using gradient descent. So here I assume that I'm at a given time t, at a given frame t, my parameters p, which I use to initialize my gradient descent, are close enough to the true optimum so that I can actually be using gradient descent. So that means that my back-warped image at a given time is close enough, resembles my reference image enough, so that I can actually use a Taylor expansion to approximate it. So let's assume that a given time t, I have my transformation parameters p, and if I do a Taylor expansion, I can approximate my reference image. So this approximation here would be the enough to minimize my my sum of square differences. So this approximation here ideally would make my sum of square differences small enough. And using a Taylor-based Taylor expansion around my current transformation parameters p is shown here by this equation, right? So from this perspective, we can rewrite the minimization problem, and instead of looking for p, I'm actually going to look for my increment delta p. So the increment from my my Taylor expansion, right? This delta p here from my Taylor expansion. Instead of instead of looking for the transformation parameters themselves, I'm gonna assume that at a given time t, I have my my transformation parameters p resemble my my reference image close enough so that I can look for the increment delta p. And all I need to do is replace the back-warped image in the sum of square differences, and that's my new problem. And this is then becomes the problem that I need to solve. Okay. So now let's solve for my increment delta p, and we can do that the same way that we've approached we can approach any minimization problem. We can look for the minimum of this function here by setting its gradient to 0. So the first step would be to find the gradient of my sum of square differences, and this is what it looks like. So it's using the chain rule. So this is the sum of exponents, and I take using the chain rule, I'll have 2 times the 2 jumps here, and I have 2 times the image difference, and times whatever is dependent on delta p inside this. So in this case is the derivative of the back warped image with respect to the transformation parameters. Okay, So now that I've determined the derivative of the sum of square differences, I need to set it to 0 so that I can find the local minimum. And setting that the gradient to 0 is shown right here, and I can just simply solve for delta p, and isolating the terms, this is what I get, which is luckily the same result that I've obtained with that original approach. So this new, well, it's not new at all, this increment here. We've achieved it from a slightly different perspective, a perspective based on a Taylor expansion. And you can check the Baker and Matthews technical report for a more mathematical derivation, which uses the same approach based on the Taylor expansion. And I think it uses almost the same notation that I've used so far here in this tutorial. Okay, so now you're probably wondering, why did I choose to derive the same update equations from a different perspective? Well, this is going to become clear when I explain the efficient second-order minimization. So in the Gauss-Newton update law that we are showing here, I've used a first-order Taylor expansion to derive it, right? But now let's consider, instead of a first-order expansion, let's consider a second-order Taylor expansion of my back-warped image to make it resemble my reference image, T. Okay? So to derive the equation over here, I've used the first-order Taylor expansion, which was basically up to here. But now let's use a second-order term and continue developing it. So just for simplicity, I'm gonna replace the derivative of the back-warped image with respect to the tracking parameters by j. So j represents this vector here now. Okay, and just also notice that j, which I call the Jacobian, is not exactly the same Jacobian that is shown in the original ESM paper. So just beware. In the original ESM paper, the Jacobian is not a function of the pixel position. It is actually just a one big matrix where the rows represent are related to the pixel position, and the columns are related to the tracking parameters, the transformation parameters, right? And instead here on my equations, j is a vector, and it's a different vector for every pixel x, and it basically corresponds to a row of the Jacobian from the original ESM paper. So this is just a side note so that you're not confused when you're reading the original paper. Okay, so I'm doing a second order Taylor expansion of my back-warped image around my current tracking parameters p to make it resemble my reference image. And in the spirits of these approximations, let me first approximate the Jacobian of my reference image t by a Jacobian of my current back-warped image with my current tracking parameters p. Okay, so this is an approximation that stands if my parameters p are close enough to the true, the optimal parameters. Okay, so if this holds, this approximation here also holds. And how is that useful? Well, it is useful because I can just simply isolate the second order term here and replace it in this original equation here. So let's isolate this the second order term and replace it here on this equation on top. And if I do that, and this is very well explained in the original ESM paper, I'm gonna get a new equation. So this equation here now becomes this one, okay, where this term h here disappears, And now I have a sum of the Jacobian of my reference image and the Jacobian of my backwarped image at the current time t with the parameters p. Okay, and from this equation here, I can isolate delta p and solve for it, and this is the equation that I obtain. And this in this equation here, the plus means the pseudo-inverse, and this here is the ESM update law, which you see in all my example C++ code. And basically the difference between the ESM update law and the Gauss-Newton is mathematically, instead of the Jacobian of the backwarped image, I sum the Jacobian of my reference image to compute the update law. And in practice, what I get is a faster convergence and a larger convergence basin. So again, this is just a very quick overview of the ESM optimization method. It's basically just a video to help you understand the code that is on my repository. And if you're looking for more information and to have a deeper understanding of the ESM, I suggest you read the work done by Selim, Benhimane, and Ezio Malice, and also put it in perspective with conjugate gradients, also the Levenberg-Marquardt approximation, and this gradient-based optimization approach is going to become very clear to you.